Well, good morning. My name is Dwayne Brown with NASA's Office of Communications. I want to welcome you, and I want to welcome the folks watching us from all over the country on NASA television. Today, you will hear about Mars exploration and the future that holds a human mission to Mars. Today's event is coming from the most visited museum in the United States, and you're going to hear more about that shortly for our official welcome. As always, you can learn more about NASA's Mars exploration program on the web at www.nasa.gov/Mars. And of course, when we talk about Mars, the social media is abuzz with communication and the conversation. Join the conversation. And normally we have one hashtag, but when it comes to Mars and the excitement, we have two. Hashtag MER10 or MER10 and hashtag 10 years on Mars. Sit back, put your seatbelts on, and let's go to Mars. Ladies and gentlemen, for our official welcome, please welcome Dr. Tom Waters.
Thank you, Dwayne. Well, apropos to the occasion, the temperature in Washington, D.C. is about the same as you can find in some locations on Mars. It's my pleasure to welcome you to the National Air and Space Museum. I'm senior scientist and chair of the museum's Center for Earth and Planetary Studies. The museum is very pleased to host this program celebrating the remarkable achievements of the Mars exploration rovers. This 10th anniversary of the MER rovers marks what I consider to be a true milestone in the exploration of Mars. The National Air and Space Museum has a long tradition in celebrating Mars exploration. It actually started with the opening of this museum and the Viking landers in 1976. We continue this tradition today with this program and the opening of a new exhibit, Spirit and Opportunity, 10 Years Roving Across Mars. I invite you all to come visit this exhibit and see the stunning, and I mean stunning, images that have been returned by the MER rovers. The MER rovers, the Curiosity rover now operating, as well as the one remaining MER rover, and the fleet of spacecraft in orbit around Mars, and those to come, promise an exciting future for Mars exploration. With that, I'd like to introduce the moderator for the first panel today, and that is Dr. Pamela, or Pan, Conrad. She is Mars senior scientist at NASA's Goddard Space Flight Center. Pan.
Thank you. Thank you all for coming here today. This is about the coolest place you can go to in Washington. And this is a really special occasion. Anybody ever buy something and about a week after the warranty expires, it breaks? Yes? Can you relate to that? So who wouldn't fall in love with two awesome robots who lasted about a bazillion times longer than they were supposed to? So that's why we're here today, to celebrate those. And with me to do that, we have the principal investigator of the Mars exploration rovers, which is Steve Squires on the end there, who's also an awesome guy, a friend of mine. Dave Lavery from NASA headquarters, who's the program executive for the Mars exploration program, who has had much to do with making the technology that has enabled us to do this in the center there, another awesome guy. And the third awesome guy immediately to my right is John Grant from the Smithsonian Institution, awesome scientist, awesome guy, and my colleague on the child of the Mars exploration rovers, Curiosity. Didn't know you were our dad, did you? And John's going to start by telling us just a little bit about the background of the mission, and we'll plunge right in so you can hear from these three guys who are really the experts. So, John, take it away.
Okay, thank you, Pan. If I could get the first graphic, please. What I'd like to say is, first of all, when we go from a parent that's a golf cart-sized object to something that's the size of a Mini Cooper, I'm curious if we really know who the parents might be there. What I'd like to start off with is just sort of a brief summary to remind you all about what the Mars Exploration Rover's mission is about. And if I could get the first graphic up, I would do that. Here we go. So as I mentioned, they're about the size of a golf cart. They've got quite a payload that you can see labeled around there. There's cameras up on the mast assembly at the top. Out on the arm, there's a couple of spectrometers that tell us information about the compositional and elemental abundance of the materials that we probe. There's something called a rat that I can't quite say with the same tone that Steve does, but I'm sure he'll say it later. It's great to hear him do it. And there's also a microscopic imager, which is sort of like a geologist hand lens that we can see the fine detailed textures. And by way of putting all that together, what we essentially get is a field geologist on Mars, something that can move around on the surface, interrogate the rocks, tell us something about the geologic setting, the environments that were there in the past, but more specifically, what the role of water was in shaping those environments. If I could go to the next graphic, please. Well, the new rover smell wore off after about 90 sols, and they kept going and going and going. And just to give you a hint, they get dirty after a while, and that's kind of what you see here. This is an image from the gallery that just opened up upstairs. But everything's still working in one form or another. There's a couple of instruments that have stopped operating in the way they were designed to. But these rovers, especially in this case Opportunity, which is continuing, just are doing a fantastic job in making discoveries and exploring the surface of Mars. Next slide, please. Well, where are they? Just to give you a reminder of where things have landed on Mars in the past. We're on opposite sides of the planet. This was really tricky during the initial operations because things were literally 12 hours apart. You could go from one floor in JPL to the other, and it was like going from India back to the East Coast of the United States. Everybody was either just waking up or going to sleep. Opportunity landed in a place called Meridiani Planum, flat plains that had a hematite signature that was observed from space. Hematite often is placed in the presence of water, so that was our sort of tempting attraction there for the rover. Spirit landed over in Gusev Crater. I almost said Gale Crater because I was confusing it with Curiosity there for a second. And what we had hoped to find there were deposits laid down in a lake from a valley that drained into the crater. We did find a number of very intriguing features related to a past history of water on Mars. I'll let Steve talk a little bit about those in just a second. Next slide, please. Both rovers far, far exceeded the shelf life, as Pan pointed out. Spirit, after landing over here to the, there's glare here, over here to the west of Bonneville Crater, went up to the rim of Bonneville and then made a beeline down towards the Columbia Hills, across some volcanic plains, and then reaching these ancient rocks that have been shaped by a number of processes, some of which included water, and we'll hear more about that in a bit. If we go to the next slide, this shows the traverse made by Opportunity. It's been going a lot longer. It's been going a lot farther. We've basically run more than a marathon now with Opportunity, starting off in Eagle Crater up there at the top, and now all the way down around the rim of Endeavour Crater, this large, mostly buried crater that allows us to interrogate rocks from beneath the plains that tell us something about the very ancient history of Mars. So with that, I think I can move on to questions or other things related to the missions. Pam?
Oh, just a couple of questions. Listen, you know, you've got a lot of work in on these two rovers, and you've done some work subsequently on the next rover. What did these rovers teach you about how to explore Mars?
Well, I have to say that the Mars Exploration Rovers, they're my first mission. So I really didn't know what to expect. And Steve, to his credit, I would say, and much to my surprise early on, approached me and said, I'd like you to be a Science Operation Working Group Chair. That gave me an opportunity that I will never forget and thank him for many times to actually get involved in the day-to-day planning. And you really have a different perspective when you understand what goes into getting the commands up to the spacecraft, getting the data back, and then repeating that process over and over again. The efficiency that's required, the teamwork that's required. Everything really has to come together between the scientists and the engineers to make it happen on a day-to-day basis. And so that process of sort of honing what we do, our skills with the rovers to maximize the science we get back is something that I really came to appreciate over the mission.
You also did a lot of work in helping select the landing site where Curiosity is. And I wonder, what did you learn from the Mars exploration rovers that helped you with that process of selecting where to go on Mars?
With the Mars exploration rovers, the landing ellipse, as we call it, the area that we targeted to land, was quite a lot larger than it was for the Mars Science Laboratory, different landing system. And because of that, the targets that we were interested in needed to be somewhat distributed. Oh, sure, we had favorites, but they needed to be kind of spread across the ellipse. So wherever we landed, we could get to the things that we were interested in. Because remember, this was only a 90-day mission, or 90-sol mission. With the Mars Science Laboratory, we have smaller ellipses, but there's also now this understanding that once you get down to the surface of Mars, you may have a little more time on your hands than you thought you did. And so the idea that you didn't have to really land on your distributed targets to guarantee the science, you could maybe land next to it and then move over to it, opened up a whole new set of landing sites that we couldn't consider for the Mars exploration rovers. And to give you an example of that, Gale Crater was actually a landing site considered for Spirit and Opportunity, but we could never get the ellipse to fit within the crater safely to make that landing happen. With Curiosity, the ellipse got smaller, and the ability or the knowledge that once we got on the surface, we had a rover that could last a little longer. We could place that ellipse next to Mount Sharp, this mountain that we're trying to get to and will get to, and then drive over to it. We didn't have to land right on top of it. So it's kind of a difference in the philosophy of how you approach the site selection.
Thanks, John.
Thank you.
So, Dave, when I first became a scientist, it was right after the time of the Pathfinder. And Sojourner was this little shoebox on Mars. How in the heck did you get from a shoebox to the Mars exploration rovers?
The process that we use to develop all the technologies and the capabilities to advance from Sojourner onto Spirit and Opportunity, and then following that onto Curiosity, is really a story that goes back easily more than 20 years. It just so happens, by accident, that I've got an example here. This is actually a spare wheel from the Sojourner rover, which landed in 1997 on the surface of Mars. You can see the size of it. And we had what were called grousers on the outside that were used to actually give us some traction in the surface of Mars as we drove. And as a size comparison, then this is a wheel from Spirit and Opportunity. And you can see how they grew in overall capability and size, just one compared to the other. I would actually normally have, excuse me, because I don't have it with me right now, but in comparison, again, that you can see the increase from Sojourner to Spirit and Opportunity. It's a similar ratio between Spirit and Opportunity's wheel up to Curiosity, which would stand about this big. But some of the technologies that were developed over the course of the intervening set of years between Sojourner and Spirit and Opportunity were full of all sorts of technology developments and advances. And actually, before I get too deep into that, I want to bring up one image, and then I'll talk a little bit about some of the technologies and what they were. If I could bring up the first image, please. One of the things that happens in the course of Spirit's mission is she returned over 128,000 images from the surface of Mars and from Gusev Crater. Out of that 128,000, this is my very favorite. And I actually went through a process. I actually looked literally at all 128,000. And you think I'm joking, but we actually did go through all of them. But this is my very favorite. And it's for a reason that might not be intuitively obvious at first. One of the things that we did with Sojourner first, and it proved out a capability, and then followed with Spirit and Opportunity, was utilize what we call the airbag landing system, which, if you are familiar with it, basically was a system where we hit the top of the Mars atmosphere at about 12,000 miles an hour relative to the planet, descended through the atmosphere, slowed down on a supersonic parachute, the heat shield fell away, the spacecraft itself fell below that, and we had a series of airbags that inflated that it then absorbed the impact shock of actually coming down and touching down the surface of Mars. The whole stack sort of bounced around for a little bit, then came to rest, deflated the airbags, and the rover and the lander were all tucked up safely inside, which then deployed. That system was first used for Sojourner, and then later on with Spirit and Opportunity. If you look at this image, on the right-hand side, you can see some discolored, sort of darker patches. Those are actually the bounce marks from the airbags as we came in and landed at Gusev Crater with Spirit. And if you take a step back, apart from the pure technology that was being used at the time and the technical implementation of what was going on, but philosophically look at this image and recognize it for what it is. Those are the footprints of a lander from Earth, from another planet, coming in and disturbing the surface of Mars for the first time. That's the physical signal that we have arrived on another planet and left our mark to show Earth is here. Philosophically, I love that image and what it actually represents in terms of the arrival of this mission on this planet, its destination, and what we're supposed to begin to be able to do for the science mission. You go to the next image. Now let's talk about some of the technology that actually was developed for these missions and what we were able to actually utilize. The big, most obvious thing is we had these rovers that were now capable of going out and traversing across the surface of Mars. Sojourner, as a technology validation mission, demonstrated the idea of putting instruments on a mobile platform and being able to move around to a destination that you saw that was interesting and possibly intriguing scientifically. That was literally a technology demonstrator to sort of validate the concept. Spirit and Opportunity were the first time we actually did that operationally. Said, okay, now we've proven that it can be done. Now let's actually go and conduct science through the eyes of a rover that can go to where we want. As part of that process, we had to think about how do you operate these rovers. What we had done up until that point in time was basically look through the eyes of the rovers, look through the rover cameras, pick a path sort of manually, and then tell the rover to follow the path that we had designated. It worked, but it was a very slow process because every time we wanted to drive into a turn or find a hazard, we had to stop, put humans in the loop back all the way to Earth, and do a full command cycle or sometimes 2 or 3 command cycles, which could take days. This image is a very important image. What we did on Spirit and Opportunity was institute a set of technologies that would allow the rover to drive itself automatically, to recognize hazards on its own, and find its own path around them. Basically some capabilities called AutoNav and Visidom and a few other capabilities that allowed the rover, instead of being commanded by humans to follow a very specific path that required the humans to avoid hazards, instead we could sit there and say, here's your destination, you figure out how to get there. And this photograph was the first time we ever had proof by looking at the rover tracks of the rover recognizing a hazard, that little rock that's on the right-hand side of the frame, and actually actively guiding its path around that hazard on its own and then continuing on to its destination. And this was about a month and a half after Spirit had landed that she was able to do this for the first time. That little sort of diversion in the wheel tracks is the indication of that. And then the last one, if I can go to the next image, that we also had, as I mentioned, this landing system that we had. The basics behind the landing system had its roots going all the way back to the early Mars missions, the Mariners and then the Viking missions, in terms of the basic technology associated with the heat shield, the parachute system, and everything else that was used to get down to the surface. The thing that we had never known up until this point with the MER missions, and this is actually a photograph from Opportunity, was we had designed these entry, descent, and landing systems. We had watched them work. We had watched the successful results, but we'd never been able to actually measure how well did the entry, descent, and landing system actually work, because we could never see it after the fact to find out, was our engineering right on? Was it out near the edge of the performance envelope? Were we about to break, or were we right in the middle of where we wanted to be? We were fortunate enough that in the case of Opportunity, we actually were able to drive up to the heat shield after it had impacted on the surface a couple months after the mission had started and we'd landed, and actually drive up to it and find it and examine it and look at the heat shield and see visibly how well it had performed its job and validate what the engineering models had told us should be happening with it. And that was actually a very interesting way of closing the loop in the engineering life cycle to do this. We didn't dwell in this area for too long. In addition to the heat shield coming down and impacting this area, there was also a metallic meteorite that was sitting right next to it. We realized that this was a place where lots of heavy metal things came down and landed, and so we didn't want to stay here for too long, so we zipped right out of here right afterwards. But there were that and many, many other technologies that were developed as a part of the process that actually enabled us to put these rovers down the surface and have them live not just once or twice, but many multiples of tens of times past their lifetime.
I gotta have that AutoNav thing for my car so I can eat a Pop-Tart on the way to work.
Actually, in a way, there are a lot of technologies that sourced and have common sources with what were flown with AutoNav and Visidom and some of these other technologies that are now making their way out into the market. I think we've all heard at this point about the Google autonomous cars that are now traversing the highways. The technology that is used on board there, in fact, some of the people who developed that technology have common roots back in the technologies that were actually flown on the Mars rovers.
That is so cool. I have more for you, but first I want to go to Steve. Steve, I have 3 questions for you. The first one is, If you had known these things were going to last longer than 90 days, would you have done anything differently during that first part of the mission?
Oh, yeah. I look back now at decisions that we made. I mean, John will remember some of this. Some of the decisions that we made. We landed with opportunity in this marvelous treasure trove of a crater that we named Eagle Crater. And, it was 45 days into the mission, and we're still tooling around in this little crater. There was wonderful science there, but I'm thinking 90-day mission, and we're going to spend we've spent half of it already in a little hole in the ground. And so I told the team, Sol 60th day of the mission, we're going over the edge and we're heading out across the countryside. I don't care what we have found. We got to get moving. And, in retrospect, today's day, 3,500 and something, I would have given them a little more time had I known.
What's the most surprising thing that Mars has thrown at you?
The most surprising thing scientifically, I think, came right when we first landed with opportunity. I did not expect that the evidence for liquid water at and below the surface of Mars was going to be that compelling, that much in our face, when we first landed. The Spirit site, we landed and what we saw was a bunch of lava. And that was all we saw for, months, until we finally reached this range of hills that we called the Columbia Hills, where we wound up spending most of the mission. Opportunity, it was all right there. I mean, just from day one. We looked, the first picture that we took, there was layered sedimentary rock right in front of the vehicle. To me, the most surprising thing with Opportunity was how easy it was. And Spirit had to work for everything.
Wow, I would never have guessed that any of this was easy, but you certainly make it sound like it. When you look in the sky at Mars and you realize that you still have tools up there and you think about what you'd like to know, what is burning in your mind that you'd just like to get the answer?
It's funny that you mentioned looking in the sky at Mars, because I was just recently down at Cape Canaveral. And I remember vividly in the summer of 2003, in the spring leading up to it, when we were about to launch, it was at a time when Mars was close to being at opposition, when Mars is close to the Earth, and so it burns very, very bright red in the sky at night. And Dave will remember this vividly, but as we were getting the rovers ready to launch, we had all kinds of problems, and it wasn't even clear we were going to get to launch. We had mechanical problems, we had electrical problems, we had all sorts of things. And we were working 12, 14-hour days, and I can remember going out onto the beach at night and watching Mars rise over the Atlantic, and it just seemed impossibly far away. And now, when I look at Mars in the sky, it's a totally different feeling. I can look at Mars in the sky at night and say, yeah, I know that place. And we all do. That's the beauty of it, is we've all gotten the chance to observe Mars, to experience Mars through the eyes of these rovers for a decade. And to me, the burning question is what it was back then and what it has always been for Mars, and that is, was there ever life there? And we don't have the answer yet, but we're a lot closer than we used to be.
I want to go back to you for a minute, John. Because you have spent so much time thinking about places to land on Mars, as well as operating rovers on 2 different missions, where do you think we should go next? No commitment here, just an opinion.
Well, I'm going to give you my diplomatic answer. Sometimes when the landing ellipse is big, there's an element of picking a landing site that's easier because there's fewer places you can go. When we started looking with the Mars Science Laboratory, the number of compelling sites that we had to consider just blossomed because we had data from other spacecraft in the Mars exploration program, the Mars Reconnaissance Orbiter, the CRISM instrument that can tell us information about the composition of rocks at the surface, HiRISE and CTX that really detail the textures and the context that we understand the geology from. We didn't have that for Mars exploration rovers. We had some pretty amazing data from the Mars Global Surveyor, but for the future ones, we had the next generation. It's hard. I've got probably a list of a dozen favorite sites. And I'm kind of holding back because I think what will happen as we start to look at the landing site process for the next rover is that we're going to get new data and we're going to have discussions with scientists and the public that is going to provide insight. And so I think, well, here's my short list, but I'm going to hold back a little bit and find out what we really learn at these sites, and then I'll pick one.
Steve, I've got a question for you. When you think about the things that you've learned using the tools with Spirit and Opportunity, and the things that you've learned, you also investigate Mars through Curiosity. What do you think is the relationship between the things you've learned with Mars exploration rovers and the things that you learn with Curiosity, and where does that send your brain for the future?
You know, I think one of the key things that we learned with Opportunity and Spirit is that there's real sedimentary geology on Mars. Before we landed with these rovers, the only kind of rocks on Mars that we really knew much about were lavas. Explosive volcanic rocks, effusive volcanic rocks, lava flows, in other words. Nobody had really studied sedimentary rocks. But the thing about sedimentary rocks is that they preserve in their details, in their chemistry, in their texture, information about what the conditions were like when the rocks were laid down. And the missions of these rovers, especially the mission of Opportunity, turned into this marvelous story of sedimentary geology, and that was what drove the selection of the Gale Crater landing site for Curiosity. Curiosity was largely designed to exploit the way in which sedimentary rocks can preserve evidence of what was going on at the time. Evidence not just of water that's preserved in the minerals, but maybe even of organic materials that can be preserved within sediments. So it sort of transformed our understanding of Martian geology.
Yeah, and as an interdisciplinary scientist myself, I certainly appreciate how fabulous an opportunity it is, if you'll pardon the pun, to understand how the materials recycle at the surface of Mars and look at those processes. And so that brings me to you, Dave. You know, it seems like all of this stuff works together. The orbital missions, the missions on the surface, until you start assembling the puzzle from the bazillion-foot view. Tell me what you think we need next to get from our robotic exploration to human exploration.
I think one of the things that you're touching on really has to do with the incredible value associated with looking how to explore Mars as a planet through an entire program of missions, rather than taking each one of these missions individually and saying, this mission is going to go and do this, and it's all going to be completely self-contained, and its data is going to be 100% complete when the mission itself ends and we stop there, and then we'll just do another one. Instead, we've structured a Mars exploration program that takes advantage of and builds and leverages upon the information, both in terms of technology and science, learned by the prior missions. And we start to extend the capabilities as a sequence of missions rather than just one individual mission at a time. That view and the idea of we have a campaign of exploration to explore Mars really has been invaluable in terms of how we both structure the missions we have and also how we incrementally increase our understanding of what the planet is really all about. That goal, and then leading to an eventual human mission on Mars, is the ultimate end goal of the entire sequence of the Mars exploration program. And that what we're trying to do is answer the series of science-based questions to help us understand the environment, what it means both scientifically in its own right, but also what it means in terms of resources that might be of benefit to a future human mission. And that set of not having just one mission to go to the planet to answer just the human questions, but rather saying we're going to incrementally increase our knowledge about those answers with each successive mission until we get to the point where we actually fly people, is the approach that we've had for the past decade and will continue to have until we eventually have human footprints on Mars in addition to the robotic ones.
And now I've been hogging up all the questions, and I think some of you have questions, and so Dwayne's going to come back up here and wrangle them.
Thanks, Penn. Yeah, of course we can't have a Mars conversation without having questions from the folks joining us here and on NASA television, and particularly on social media. For folks here, there's a microphone. Please make your way there. And, of course, join the conversation, ask questions, 2 hashtags, hashtag Mer10 and hashtag 10 years on Mars. Just a reminder also that this event is being live streamed and archived at www.livestream.com/Mars. My first question, and I have my handy-dandy little phone here. I think this is going to be for Dr. Squires. From the social media world, it's pretty cold in the nation. Extreme temperatures, and there's some buzz on the social media site that how could this compare to the temperatures on the red planet?
This would be a nice warm day on Mars. The average temperature on Mars today is about minus 60 degrees Celsius, so way colder than any place in the United States right now. In the middle of the day on a warm, sunny summer afternoon, it might get up to about 0 degrees C. But Mars is a really cold, nasty place compared even to the coldest, nastiest place that you can imagine in the United States right now.
Okay, let's take some questions here. Again, I'm going to thank the National Air and Space Museum for hosting us. And first question, sir.
My name is Mark Goldberg, and I'm a docent here at the Air and Space Museum. My question is, given the increasing sophistication and success of the robotic missions, what is the goals that would justify the risks and costs of sending a human to Mars?
I'm going to give you a partial answer with a promise that if we want to pursue it with some of the people who are going to be more qualified to give you an answer about the human missions, we can make that contact for you afterwards. But fundamentally, NASA has been given the goal of, in the long term, having a human mission to Mars. And there's a couple of different reasons that we are pursuing that goal. One, it is part of the national space policy and part of the reason that the agency now has in its charter to continue to explore. But fundamentally beyond that, it's part of what we've always considered a human imperative of exploration. We have long sought to expand human presence beyond Earth in a permanent way. And Mars is basically the first stop on what will eventually be a solar system-wide and hopefully well beyond that journey of exploration with human presence. Mars is the one that's beckoned to us from the very beginnings of our understanding of the solar system and been so intriguing to reach out and try to grab that it's the place we want to get to next to explore, and will be the one that we'll get to first because it's just the next stepping stone to get out into the solar system.
So the itch of exploration.
Exactly.
Next question.
Hi. Thanks to the panel. I'm Joe Mascaro. I'm a fellow with the American Association for the Advancement of Science, and I'm currently at the U.S. Agency for International Development. My question is about the kind of perceived competition between the robotic programs and the manned programs. And I'm really curious to know if you think there's possibility of hybridizing the robotic and manned programs. I know the fans of both programs are obviously really not in competition with the other program. We'd all like to see sort of the robotic and manned programs move forward simultaneously.
I'm going to start the answer to that one, and then I'm going to let Steve answer it as well. But I'll just say, from the standpoint of someone who builds robots for their career, and I'm a roboticist by background, and that's what I've done even before I got into the Mars program, I can't imagine anything better than human footprints on Mars. The robots are there as precursors, and they are there as the tools paving the way, and we use them now because that's all we can do at the moment. But there's no misunderstanding that our long-term real goal is human exploration of the red planet. We use robots as tools to help us get there, to figure out the best ways to make that happen. But we are, as roboticists, massively excited about what we can do as people as well. I think Steve can talk in particular about rates of exploration and effectiveness and throughput of science and things like that that really are enabled by human presence.
Yeah, I'm a robot guy, but humans can't get to Mars soon enough for me. I did an interesting experiment once. We were out in the field with one of our test rovers, and it was exploring around, and I had some geologists with me, and I would watch the human geologists do their thing on Earth, and then I would time how long it took them to do things, and then I'd convert that into equivalent time for a robot. And what our magnificent state-of-the-art vehicles can do in a day, these guys could do in about 30 seconds. So I'm a huge, huge fan of human exploration.
Okay, we're going to take question. I think we have a young person here that may be that human person that goes to Mars, and we have a panel coming up that's going to be talking about that. Yes, young man.
Hi, my name is Xavier. I'm from Virginia. Are you sure there was water on Mars?
Are we sure there's water on Mars?
Yes, we are sure there was water on Mars. A geologist is sort of like a detective at the scene of a crime. You're looking for clues, and the clues are in the rocks. And Spirit and Opportunity, our two detectives, have been looking at the clues in the rocks for 10 years now, and the clues are certain. There's no question there was water on Mars, and plenty of it.
Okay, let's go to social media. We've got time for a few more questions, and we've got another panel coming up. This is from @Shadow404, and certainly for Dr. Squires and others. What, in your opinion, are the most amazing discoveries from Spirit, Opportunity, and Curiosity so far, and why?
I think the most important discoveries from Spirit are that at the Spirit site, we see evidence of early Mars that was a hot place, a violent place. There were volcanic explosions. There were impacts. There was hydrothermal activity. There were steam vents. There may have even been geysers coming out of the ground. At the Opportunity site, we see evidence for ancient water that was beneath the ground. It was acid. We run around saying water on Mars, water on Mars. It was really sulfuric acid on Mars. And it leached stuff out of the rocks, and then it came up to the surface, and it evaporated away, and it made these fantastic salt deposits. At the Curiosity site, we see evidence for water at the surface, but it was water that wasn't acid. It was water you could drink. It was water that would have been an environment that would have been really favorable for life.
Water you can drink.
You could have.
Whoa.
Not anymore.
Okay, final question from social media. And keep those questions coming. We have another panel. Maybe we can get those answered, or we'll get them answered later. At Libby Doodle, I wonder which is crazier, airbag landing or sky crane landing?
It all depends on how you define crazy, I think. Yeah, Steve's right.
It's only crazy if it doesn't work.
Yeah, they both worked, and so, how crazy are you? I will just say that the first time that we all saw the airbag concept and we understood really what was going to be involved with it, so we're talking now back in the early 90s when the idea was first being discussed, and then immediately as the idea of the airbags was being presented, it was also accompanied by the comment, oh, this actually is an idea that goes all the way back to the mid-'60s and an idea for a lunar lander that had come out of Russia. And we all said, maybe there's something to this. Okay, let's study this some more. And we sort of got past the wow factor pretty quickly and then realized that this is a very viable idea. And from the engineering standpoint, it all worked quite well. And we got past that. When we started talking about the sky crane for Curiosity, it was maybe a little bit of a different story and a different reaction. I remember the very first time that it was sort of presented to a large group of the engineers by the people who had developed the concept, where we basically took the entire thing that we would typically have as a lander and flipped it on its head and did everything backwards and upside down. And I think the first reaction from most of the room was, wow, the 60s were really good to you. But then again, once you decompose it and you took it all apart and you understood why you were doing each of these things in a backwards, upside down way, from an engineering standpoint, it all made sense. So yeah, there was this initial "are you out of your mind" factor that went along with it, but very quickly we realized it was all very logical and it made sense given the problem that we had been presented with. And so, and then as I say, the proof is in the pudding. It worked in all the cases so far.
Okay, so the last question here, and I've got 1 minute, but this is so important, and I'm going to ask the director to give me a couple of more minutes here. And a quick answer from everyone from @AlexCG. What can citizen scientists and the community do to help with Mars exploration?
They can do a lot of things. In fact, we've got programs involved with some of the missions where the data analysis, things like counting craters on the surface, counting rocks and their shapes and their numbers, tell us something very fundamental about the geology and how the surface has been shaped. The public is involved in that. There's a variety of ways that people can do that. but just looking at the images, becoming a scientist, exploring the surface of Mars with us. I can't tell you how many websites there are out there where you see people that are literally following along with these missions as we as scientists are working on them. And by golly, they're coming to the same conclusions that we are. These people are involved, they're looking at the data, they're learning, they're understanding Mars, they're understanding geology. So I think there's a variety of ways to get involved, and I think those ways lead to very, very worthwhile and important results.
And the one thing in particular I'd like to point out in addition to that is, as John mentioned, there are several different methods by which the general public can be involved, but also we have a couple of very targeted activities and portals for student involvement, both formally within the classroom as well as informally at home. We are actively constantly seeking out opportunities and have presented a lot of opportunities for student participation, doing things, as John mentioned, like crater counting, but doing various different experiments to understand what you're actually able to see in the images. Looking at data associated, for example, with the Spirit and the Opportunity rovers, we have these little sundials on board, and actually presenting information that allow a student to take a look at the sundial and the shadows and determine by back solving where is the rover on the surface of the planet and relative to the angles of the sun that are coming in and things like that. So there are all sorts of different activities, in particular targeted at student involvement, ranging all the way from very low elementary school grade levels all the way up through undergraduate student levels at college, that will allow an even more in-depth level of participation.
And I think finally there's another element to the student involvement in particular. Those of us who built these rovers, many of us grew up in the 60s and the 70s watching Mercury and Gemini and Apollo on television and dreaming of sending spaceships to Mars someday. And then we got to do that. And I hope that part of our mission's legacy will be that young people will look at these rovers that we built. We'll look at the videos of us jumping up and down on landing night like we just won the Super Bowl, and we'll think to themselves, that's really cool, but I bet I could do better. And if that's part of the legacy of this mission, that'll be one of the greatest things I think we could have accomplished.
Ladies and gentlemen, without further ado, please give these folks and the team of thousands, 10 years on Mars, the MER team. Wow, 90 days to 10 years. What you guys know how to build things. Made in the USA, right? Okay. Don't change that dial. We have another panel coming up. You're going to see folks moving around, and you heard humans to missions to Mars. That's coming. Stay tuned. The panel, and there's a young lady who is really serious about being the first person on Mars. So stay tuned. Remember, keep those questions coming. This is being live streamed, www.livestream.com/Mars. Go to our website, www.nasa.gov/Mars. The iconic, coming to you from the iconic Smithsonian National Air and Space Museum. Our second panel, Tom Waters is going to come back and talk to you more. There's also a new exhibit that opened. Perhaps Tom can talk to you about that. Don't touch that dial. The second panel is coming momentarily. This is NASA. Dwayne Brown, stay tuned. Tom?
Well, again, it's my pleasure to welcome you all here again to the National Air and Space Museum. The program has been fascinating for me as a scientist, a planetary scientist, and someone who's worked on Mars. I'm never, ever left without just being amazed by the discoveries of those two rovers. And again, I want to invite you all to come to the exhibit that is opening this week and just view the absolutely stunning images that have been returned by the MER rovers. With that, it's my pleasure now to introduce the second moderator for today's program, and that is Dr. Jim Green. And Jim is the director of NASA's Planetary Science Division, and I want to say a real true friend of the National Air and Space Museum. Jim.
Well, thank you very much. This is just a fabulous venue to be able to talk about what we're learning from Mars today. But this panel is really about the future. What are our plans on Mars? What are our next steps? And I am delighted with the panel that we have here today to be able to talk about this. On my right is Dr. Mary Wojtek. Mary has got a number of degrees in biology, biochemistry, oceanography, and just a fabulous person to study microbial life and life beyond Mars, or pardon me, life beyond Earth, and beyond Mars too, you bet. She is the head of our astrobiology program, and she goes to work every day and talks about how do we look for life and what do we need to do next to be able to determine if there is life beyond the Earth. Sitting next to her is John Connolly. I've known John for many years. John is based out of the Johnson Space Center, and he is the chief exploration scientist working in the Human Exploration Directorate at not only JSC, but comes back to NASA headquarters and works with us a lot. John's been involved in architecting how we would get to Mars through a variety of what we call design reference missions for a number of years. So if anyone's going to help us get there for humans, it'll be John Connolly. Sitting next to John is Dr. John Grunsfeld. Dr. Grunsfeld has been at NASA headquarters for the last 2 years, and he's the Associate Administrator of the Science Mission Directorate. John began his astronaut career in 1992, making 5 flights. And in those flights, not only did he have an opportunity to crawl around the Mir space station, but from a scientific perspective, and one close to my heart, he was able to be on 3 Hubble upgrade and repair missions. And of course, Hubble is just such a fabulous asset, not only for astrophysics, but in planetary science as well. We use it a lot. Now, sitting next to John is really the next generation of explorers. This is Elisa Carter. Elisa is our first winner of the NASA Passport Program. I know she'll tell us all about that. She's from Louisiana, and she speaks several languages. And of course, from her perspective, and ours too, she wants to be that next person going to Mars, that first next generation on Mars, that first human to walk on the surface of Mars. So with this distinguished panel, let's talk about the future. But before I do that, and if I have my first slide, I want to talk about some of our operational assets that we have today. We've learned a lot about Opportunity, which is still operating on the surface, and of course, Spirit, which didn't survive our last couple winters and is not probably going to come back to life. Opportunity is working fabulous, as we've heard. But we also have another rover on Mars. It's called Curiosity. In Curiosity, Mary has been very much involved in some of the data and some of the activities there, and we'll have an opportunity to talk a little bit about her perspective on Curiosity. But what really helps make those rovers work is our orbital assets. We have 3 orbital assets there currently, and they are Mars Odyssey, Mars Reconnaissance Orbiter, and Mars Express. And these are the guys that help support not only the rovers on the ground and our landers that we've had in the past, but they also make fabulous measurements from space of the areas that the rovers are moving into, and actually look now also for upcoming sites. And as John Grant mentioned earlier, there are plenty of sites and exciting sites to go to on Mars that will also enable us to learn much more about that environment and move forward. Recently in November, we launched MAVEN. MAVEN will arrive at Mars in September of this year. MAVEN is also going to join our orbiter assets, but it's going to look at the interaction between the solar wind, the ionosphere, and the atmosphere of Mars to see what it's like in a planet that has no magnetic field. It's going to allow us to make a lot of comparisons between what Mars' environment is like and the Earth's environment, and why they are so different. Now, the future we'll talk about a little later on, but those are the basic orbital assets that I wanted to start with. Now, what are our next steps on Mars? How will humans be able to make those plans and execute those plans over the next several years? And what are the burning questions that we want to know? Well, first, from a scientific perspective, we really want to know, is there life on Mars? Is there life? Can life exist beyond the atmosphere of the Earth? And so for that, I'd like to turn to Mary and have her give us a little explanation of what we're up to in that area to determine and understand these basic, answer these basic questions.
Thank you, Jim. Can I have the first slide? So I'm going to tell you about astrobiology. It's the program that I run. I'll begin by telling you what it isn't. It isn't science fiction, and it isn't alien autopsies. What it is the study of life in the context of the universe. And we focus on three fundamental questions. How did life begin and evolve? Does life exist elsewhere in the universe beyond Earth? And what is the future for life here on Earth and beyond? It's a program that's been ongoing at NASA since the mid-'60s, addressing all of these questions. Now, one of the aspects of astrobiology is that we only know of one place in our universe, in our solar system, where there is life, and that's here on Earth. So we begin our study to understand the potential for life elsewhere by understanding as much as we can about life here on Earth. Next slide. So what have we learned about searching for life by studying the Earth? We've learned that they're really tough. You find life almost everywhere we look on this planet, and I'm going to talk a little bit about those extreme environments and those extremophiles, those that like those extreme environments. Life is tenacious. It survives for many, many generations under severe conditions. It's metabolically diverse. It eats everything. It breathes anything. And when conditions are extremely tough, life moves inside the rocks. Next slide, please. So I'm going to go through what I call the X-files, or extremophiles, and just tell you about the record breakers for each of these categories. So up in the left-hand corner of my slide, there's a picture of the Grand Prismatic Spring in Yellowstone, and the temperatures in this environment exceed boiling. And the highest temperature that we've observed organisms growing, and of course these are microorganisms, is 121 degrees C. Water boils at 100 C. And I'll just point out that extremophile, or an extreme environment, is an anthropocentric definition. It's an environment that we as humans don't think we would like to live in or could even live in. But in fact, there are organisms, microorganisms on Earth that do just fine. Now, the coldest, these are examples of places in the Arctic and Antarctic where organisms can live in ice or at temperatures below freezing. So the record for cell replication, or the increase in growth in cells, is minus 15 degrees C. And remember, water freezes at 0. Metabolism is even lower. You can get it to minus 20, and we have found cells that survive for decades, even millennia in permafrost, where temperatures can reach minus 40. Next slide, please. Okay, the next one. There's no more? No, I had 5. All right, well, let me tell you about some other extreme environments. We have records in acidic environments. So everyone knows that a neutral pH, or what our water tends to be, around 6 or 7. The ocean is 8, a pH of 8. Battery acid is a pH of 2. Coke is a pH of 3. And we have organisms that can live at pH 0. Not us, microorganisms. The other end of the spectrum, high pHs, this is something we call basic environments. Lye, the stuff that you use to remove hair and fur when you're tanning leather, is something like 12 or 13. We have organisms that can live in a pH of 14 at the top of the scale. Again, microorganisms that have adapted to these incredible environment. In addition, we have organisms that are able to withstand really high levels of radiation. We've isolated organisms from cooling towers at nuclear power plants. We've isolated one of the most famous organisms, Deinococcus, from inside a can of Spam. Now, what was it doing inside a can of Spam? It was part of a set of experiments looking at how you could preserve food using gamma radiation. And it was able to exist and grow even after Spam had been irradiated a number of times with gamma radiation in very high levels. These organisms withstand irradiation that's on the order of 10,000 times what we as humans can withstand. And then finally, organisms are able to withstand really, really dry environments. These are called xerophiles. And one of the ways that they survive it, and unfortunately I can't show you a picture of it, is they move into rocks. So in the dry valleys, which is one of the driest places on Earth, of Antarctica, you find organisms actually living inside of rock, able to make a living, to grow to a level where you can actually visibly see a band of color where they can grow in this rock. So this is where we begin our search in defining what the limits to life are here on Earth in order to understand the type of environments that we can look for, those environments that are habitable, that could be located on Mars or other places in our solar system and, of course, beyond. And I think I'll just stop there for now and let other people speak.
Well, let me ask you then, in terms of Mars, we know, as we talked about today, the extremes in temperatures. You know, even though we think it's cold here today, it's actually that temperature is some of the higher ranges of temperatures on Mars. So going to Mars, knowing that if life does exist there, it has to live in extremes, how would we identify that? What are the signs that we need to seek to be able to determine if there's life there?
Well, I say just in general, our strategy has been, and our missions reflect this, is to look for some of the fundamental things we believe life needs. So for a long time, our mantra was follow the water. And as our young future scientist and Mars explorer asked earlier, do we really believe that there's water or was water on Mars? And of course the answer is yes. We have lots of evidence of that. So we know that there was water. We've had missions that looked at those habitable environments where we know that there are the kinds of chemistry that you would need to build life, the kinds of environments that could support it, temperatures that exceed the lower limits. And we find places like that on Mars as well. And so now we're getting a better sense of where on Mars we might look for existing life. And one of the most promising, at least currently, the most promising places to look is, as I mentioned, life takes cover when things are really bad. And we believe that the harsh environment on the surface, really dry, high radiation, may drive life today if it exists underground. And that would be a place that we would look. Now, what would we look for? We already know that if we've landed there, taken a lot of pictures, and there's something with a face and waving, we could probably say that that's life. But it's more likely that it's going to be microbial. So we would start looking for morphology that looked like a microbe, which is microscopic, or the chemistry that microbes would need to exist or would use to build their cell walls and all of their cellular machinery.
Okay, that's great. So now, based on our next set of missions and working in this particular area, we're getting ready for human exploration because we need to know everything about Mars before we send humans. You know, human exploration is not really Star Trek. It's not go where no man has gone before. And so that means scientists, planetary scientists, are leading the way. But of course there's a synergy here. You know, human exploration also needs information. And the kind of information they need is sometimes very different. And so let me ask John if he would talk about that next step on how we're merging science and exploration and what are the kind of technologies that we're looking at to support missions to Mars for humans.
Well, thanks, Jim. I think if we bring up the first image I have, this is one of my favorite images that maybe illustrates how I feel about the merge between human exploration and the kind of robotic science that we're doing right now. This was a painting done by one of our fine space artists, Pat Rawlings, and this shows a future astronaut finding the site of the Pathfinder rover, much as Alyssa may find the site of the Spirit rover at some point in the future. And I think this is the essence of the relationship between human and robotic science exploration right now. The robots that we put down on Mars, both on the surface and in orbit, are our avatars right now. They are our our eyes and our hands and our feet on the ground that are informing us how to get ready to eventually send people there. There are a lot of unknowns about Mars, and without the robots going there first and finding out a lot about these unknowns, it would be a very, very risky endeavor to send people there. If you go to the next image, this kind of shows where we are today and where we want to go in the future. Now, I could spend a lot of time talking about Mars mission design. I've done a lot of thinking about that, but I wanted to focus a little bit in on how these robotic missions help us out, because they're really an important piece of the entire plan. Right now, we have the International Space Station. It's been crewed for over 13 years continuously. We're learning lots about how humans survive in space, what we call human health and performance. That's a big step. That's a big unknown. How will humans handle that 500 to 1,000 days of a Mars trip? The other big unknowns have to do with Mars itself. What's the radiation like on the surface? Is the soil toxic to humans? Are there resources there we can use? There's lots of what we call strategic knowledge gaps, and the robotic missions are our way to fill in a lot of those strategic knowledge gaps. And then thirdly, there are new technologies. Going to Mars with humans is going to involve technologies that we're trying out on robotic missions and some that we haven't even developed yet. Luckily, we're starting to learn about things like how to get through the Mars atmosphere and land, the however many minutes of terror. It's going to be shorter with the human mission, by the way. It'll be about 3 minutes of terror. And learning how to use the resources on the surface. So there's these three big unknowns, and in at least two of those areas, the robotic missions that are on Mars right now are helping us to answer those questions. And then finally, one last image. A wise man once said that science enables exploration and exploration enables science. And that's absolutely true, and that's how we feel about the merger between the science that we do at Mars right now and human exploration that will follow. In fact, it's very hard to put a science instrument on Mars, on one of these rovers or in orbit, and not give us some information that will help us eventually with humans going there. And as it was stated before by Steve Squires, I think once we get humans to Mars, the science was just going to go up by orders of magnitude. So these missions that we have on the surface right now, Spirit and Opportunity, Curiosity, and Pathfinder, those are a legacy of great science that's going to eventually help get humans there.
Thank you, John. Now, of course, as discoveries are being made by Spirit and Opportunity, our orbital assets, Curiosity, and that information is coming back. What is the most surprising thing that you've learned that then changes the design or changes the way or approach that we would implement to put humans on Mars?
Looking back at the robotic missions in the last 20 years, the discovery of large amounts of water, I think, was the most satisfying finding, because that changes the equation entirely about how you explore Mars. Water is like finding gold. It is the most precious resource out in the solar system that you can imagine. It is the stuff of rocket fuel. It's the stuff of life support. Hydrogen and oxygen are those building blocks where you can make a lot of other things out of. And so finding that there's large amounts of water on Mars was probably the biggest finding from the robotic missions, and the one that's really changed our thinking about how we would eventually send people there.
So instead of carting all this water, we can tell you, bring a straw, because we know where it's at, or how to get at it anyway.
Not only water, but rocket fuel, which is about 80% of the mass of everything we launch into space.
That's great. Thank you. Well, let me now turn to John Grunsfeld. And John, of course, as the Associate Administrator of the Science Mission Directorate and oversees our major program in Mars, we've worked hard together over the last several years that you've been here to chart that course. What is our immediate future on Mars relative to science, and then how would that lead into exploration?
Well, let me make a few comments about Curiosity, about Opportunity before we get there. But I shared an office with John, and we've had many, many discussions about how to get to Mars. And that famous saying, we would often have the discussion, well, exploration is science, and science is exploration as well. But I had the very good fortune to be at the Jet Propulsion Lab for opportunities, entry, descent, and landing. And it was obviously a very tense time, and I was standing next to my predecessor, Dr. Ed Weiler. And of course, at one point I had to be a smart guy, and I said, Ed, it's already happened. We just don't know the answer yet. But it really was amazing to actually have radio signals of the little rover tight in its bouncing ball as it was bouncing on the surface. And the communication with the rover kept going in and out, and somebody realized, yes, we're watching it bounce. Just phenomenal. And of course, at that time, we thought we had a 90-day mission. And so again, being kind of a smart guy, I said, hey, Ed, how long do you think it would take Steve Squires to do the same thing on the surface of Mars if he was there, of everything that the rovers will do in 90 days? And Ed came up with an answer which was, a week or something like that. And I said, I bet he could do it in 4 hours. And Ed got mad at me. So then Steve came in from, all jubilant, and I said, hey, Steve, how long would it take you to do the 90-day mission? He said, about 20 minutes. And that's really one of the drivers, is that we are so capable, and working with robotics, working with our scientific partners, we're all that much more powerful. But the one perspective that I want all of you to leave with is the really shocking revelation from a NASA official that Spirit, Opportunity, Pathfinder before it, and Curiosity now on Mars will discover nothing. They're just our tools. It's people, it's scientists here on Earth that are making all the discoveries. And we shouldn't forget that. It's great, to think of Opportunity as our friend, as our robotic assistant, as our avatar. But it's a scientific tool. And I think it won't be until we get people on Mars that the big transformation in both science and also humans as a species will occur. However, we have to go one step at a time. And so we do have Opportunity still running after 10 years. That's phenomenal. Steve could reflect on how long would it take him to do 10 years. And it would have been a good question, but you can kind of extrapolate. Curiosity is now roving, and I asked John Grotzinger, the project scientist for Curiosity, the same question, same answer. If only I was on Mars, we could make progress much more quickly and get answers to those critical questions. And Curiosity's question was, did Mars ever have an environment that we would know would be habitable if there were microbes there? And of course, like Opportunity, we landed in a spot where we were able to answer that question right away. We now know that Mars had an environment some billions of years ago that could have supported life, that had liquid water with neutral pH. You could have put a cup in the water and had a nice drink. And if you were a microbe, you could have thrived in that water. All of the nutrients that you would need. Temperatures that were above freezing, that you would have liquid water. Probably a dense atmosphere, clouds, rain, snow-capped mountains. Really quite a nice place. Now we're able to use Curiosity and drive towards the flanks of Mount Sharp to figure out, well, what happened, hopefully, and using the MAVEN spacecraft that's on its way to Mars to figure out, how is Mars losing water and its atmosphere now, so maybe we can use all of the resources we have between Curiosity, looking at the sedimentary rocks and trying to trace back the atmospheric history of Mars back billions of years, MAVEN looking at the atmosphere today to figure out what happened. Why isn't Mars a nice place for human life now, so that you'd have to be in a spacesuit? Now, personally, I love working in a spacesuit. It's actually the most fun thing I've ever done. So that doesn't bother me at all that when we go to Mars today, we'll have to wear spacesuits. But at one time, it wouldn't have been necessary. We're getting ready to send another mission to Mars called InSight. It was a competitive mission in our Discovery program. We have looked at Mars with the Hubble Space Telescope, studied its atmosphere with the Space Telescope imaging spectrograph, and of course imaging. We have orbiters around Mars that have studied the surface in great detail. One of the big questions, actually, when we sent Spirit and Opportunity to the surface was that we looked at Mars and we saw a planet that looked pretty simple from space, more or less. Would we discover that Mars had a very complex history and lots of surprises. And of course, within just a few days of landing, Spirit and Opportunity figured out that, yeah, in fact, Mars really is a much more complex planet than we ever imagined, and had a lot more geologic processes than we could see from space. And Curiosity is now confirming that even further. But we've never looked inside of Mars. Of course, on Earth, you walk around and you put little seismographs, and you can learn a lot about the inside of the Earth. That's how we figured out, that we have a crust and a mantle and an iron core, and the circulation of that creates our magnetic field. Well, as you heard from Jim, Mars has lost its magnetic field. Has Mars cooled off completely, or is there still some volcanic processes going on? Well, we're going to put a geophysical monitoring station on the surface of Mars. It's going to put a heat probe in the surface to learn about what's the conductivity of heat through Mars' surface. Is it still cooling off? And a seismometer to see, is there still seismic activity? Is there some analog of plate tectonics, of faults, scraping against faults? And when Mars gets hit by meteorites, which it does all the time, we'll be able to see the planet ringing and map out the interior. We're also partners with the European Space Agency. They're sending an orbiter in 2016 and a lander in 2018, and we have experiments, mass spectrometer on the lander. And then in 2020, we're sending a brand new rover to the surface. It may look a little bit like Curiosity, but that's because, rovers, all cars kind of look alike, but what you do with the car could be very different. But this is entirely a different analog, which is the rover will have similar driving system and wheels and a deck and a similar power supply, but all the experiments will be brand new, and that's the exciting part. And I'd love to tell you what those experiments will be, but we don't know yet. Next week, proposals will come into NASA from around the country, and in fact around the world, for the best ideas on what new science to do on this rover. And we've only just scratched the surface, literally, of Mars in all the interesting places that we can go. In fact, the most interesting places of all are where we currently think we see liquid water leaking out, or where the interface between ice and the surface, where it melts, because Mars has polar ice caps and it melts and thaws just like on Earth. And so those places, though, we don't want to go yet, because if there's life existing on Mars today, we don't want to hurt that life. So we have this grand plan going out through 2020. The Mars 2020 rover should last a number of years. We're going to plan for it to last at least 2 years. So I think we have at least another decade of plans on the books now for amazing Mars exploration that may tell us about signs of life on Mars if it exists, certainly about past life on Mars if it existed. And so the story is still wide open. And for the first time on the Mars 2020 rover, a significant fraction of the payload is being done in cooperation between human spaceflight and the science spaceflight, which personally I see as linked, because that's how I've lived my life. And as I said, all discoveries are made by humans, not the rovers. And so it's a very exciting future, so that when, Alyssa, you go to Mars, you're going to know a lot before you go.
That's right. In fact, Seeking Signs of Life is sort of the plan that we have for that rover, for that 2020. It's going to core. It's going to create cores, and we're going to be able to interrogate them and put them in sleeves and put them in a cache for later analysis. So it is a huge leap and very much different than Curiosity. And, of course, hopefully, we're going to want to continue to do science analysis and bring those samples back.
Well, I'm counting on Alyssa to bring them back.
That would be great. That would be great. So, Alyssa Carter, you're our next generation. You're that Mars scientist that we hope will be walking around and doing those geological experiments and reporting back. So why don't you tell us a little bit about what's been happening in your life?
Ni hao, bonjour, hola, hello. My name is Alyssa Carson, and I've been trained to be an astronaut for 9 years. Currently, I'm 12 years old, so I kind of started at 3. I basically decided at 3 that, okay, being an astronaut, that sounds really cool. And then I learned that we have only been to the moon, so I set my sights for Mars, and I haven't changed my mind since. I attend the Baton Rouge International School, and there I speak 4 languages, English, French, Spanish, and Chinese, and I hope to learn Russian soon. I've been to Space Camp in Huntsville 11 times so far. Usually I go about twice a year. I've also attended Space Camp in Izmir, Turkey, and Space Camp in Laval, Canada. So with attending all these space camps, I have become the first person to complete all the space camps in the world. Also, I have completed the NASA Passport program, so I have visited all the NASA Visitor Centers in the U.S., which is 14, so that includes this one. I've been to multiple Sally Ride day camps, so around my area we may have a day camp and you go and you get to learn all about math and science and do different experiments. I've also done the week-long camp at MIT, so we basically did a week-long camp and we learned about marine biology and also different sciences. I've witnessed 3 space shuttle launches, STS-132, 134, and 135, which all were amazing and successful. So I have completed all the space camps and completed the NASA Passport program, basically because I would like something unique on my resume for when I apply to become an astronaut, because I would like something to help me stand out, so to make me kind of pop out to be a major option. So that's kind of the main reason I also did this, and both doing all the space camps and completing the passport, it was all a lot of fun, especially since I completed the passport program by doing it on a road trip. So that was interesting, but also very fun. As college goes, I plan on attending either Cambridge or Oxford. After that, most likely International Space University in France, and then attend MIT, and I hope to get a degree in astrophysics. So, a lot of studying to do there. But, I don't know, I guess I've always had this dream, and I just follow it as best as I can, no matter where it takes me. So, I've been to Izmir, Turkey, which sounds like such a strange place, but it's part of my dream, and so I follow it wherever it takes me. I am the Mars generation.
Yeah, absolutely. And you've convinced me. And, when you talk to kids your age, do they seem to be excited about Mars? Do they seem to be excited about space? Or is it, even a tenth of your excitement?
I've talked to many groups of kids, and most of them, they have lots of intriguing questions. After I'm done and I ask for questions from the audience, they all seem very interested. They're all excited, wondering where we're going. They're asking what NASA's doing now. They're asking all sorts of questions, as in, what are we doing now? Also, how space travel works, as in, just some simple questions that would be simple on Earth but get complicated in space, as in showers. They ask about, how life is different on the ISS. But they're all excited. They're all excited about going to Mars and sending that next generation.
That's great. And I want to tell you and encourage you, follow your dream.
Thank you.
And I think with that, let's ask Dwayne to come up and see if we can answer some questions from the audience and social media.
Yes, it's Q&A time again. And if you're just joining us on NASA television, please, this is the second panel, the first panel, talking about 10 years on Mars. No worries. This program is going to be archived at www.livestream.com/Mars. We are coming to you from the most visited museum in the United States, the Smithsonian's National Air and Space Museum. 2 panels talking about Mars. We're going to get some questions here. And a reminder, all of the data from the Mars exploration program, Curiosity and Mirror, all of that data is available to the public. Available to the public, to you, It's all about Mars. It's all about us. It's all about the future. Okay, so let's get with the Q&A. We're getting a lot of questions from social media. Again, 2 hashtags. When it's Mars, a lot of conversation on social media. Hashtag Mer10 and hashtag 10 years on Mars. I'm going to ask folks to join us at the mic, but I'm going to take one question actually from our live stream. This is probably for John Connolly. How simple would it be to turn water on Mars into drinkable water for astronauts?
Well, actually, we have that technology. Water processing technology is pretty well known, and the missions we have on Mars right now are telling us a lot about the pH of the water and what kind of minerals might be dissolved in it, and I think it would be relatively easy to make a drinkable glass of water on Mars. That would be one of those big historical moments, the first time a human being took a drink of water that was not from this planet.
Okay. Next question is for our young human, first human to Mars person, Ms. Carson. And I think you already answered this, but you've excited a lot of young folks watching the program. And they want to just say, you talked about your dreams, but what advice would you give them if they too want to be inspired and be sitting up here with these incredible people? What advice would you give the young folks out there?
Well, I would tell any child that are looking for a dream or something that really interests them, I would tell them to find subjects that you're interested in and pick a career that goes along with the subject you're really interested in, because you really want to love your career. And if you're finding your dream, you know, just stick with it no matter what obstacles get in the way. And don't let anyone tell you that you can't fulfill your dream. I've been doing trying to fulfill my dream since 3, and I'm still going, and I do not plan on stopping. So just keep on going and never stop believing in yourself, and don't let anyone else bring you down.
Thank you. Okay, let's come to the mic. We're coming back to the National Air and Space Museum. Go ahead, sir. You talk up a little louder. Keep going.
Okay.
Well, my main role model is basically just all astronauts because they all inspire me. So, here's one right here. But at my school, we also learn cultures because with all my languages, my teachers are from the country that speaks the language. So they try to tell us about the cultures, the language, their traditions. So I've gotten used to some cultures, and so with that has really helped me become accustomed to most different cultures, and I'm pretty used to transitioning to different cultures, because at my school you may be in Spanish class and you're doing a Spanish culture, then all of a sudden, oh, it's time to change class. Now we're going to France and we're doing a French culture. So you kind of learn to transition pretty well at my school between cultures and different languages.
Next question.
Hi, my name is Shauna, and I live here in D.C. I actually work here at the museum. I'm an educator, well, geologist turned educator. Alyssa, you give me so much hope for the future, and I am also a big astronaut fan. Sally Ride was my hero growing up. So I was wondering, what are 2 traits that you've seen in the astronauts that you admire that you're working on cultivating yourself as you prepare to become one?
2 traits that I see would be bravery, because we all know there are dangers in going to space or going to any planet. Yet, in my opinion, the benefits outweigh the risk because it's just such an adventure. Also, I guess loyalty to your crew members. Having to be, be friends with people that you're going with, because all astronauts, they just become one big happy family. And it's just, I don't know, I guess all the astronauts, they just become family, and they all trust each other with each other's lives, basically. And I guess that's a good thing to have as a trait.
Any other questions from the audience? Okay, we'll go back to social media. We have time for a couple of more. This is from @Terry Universe U, I believe. For the panel, where is the most habitable place on Mars based on current scientific discoveries?
Well, as Curiosity has clearly demonstrated, it actually has landed in an ancient riverbed. And so we now, from orbit, can take a look at other similar locations and recognize that there's been a fair amount of water on Mars in the past, oceans of water, perhaps. And that water has carved out gullies and valleys. And so from a habitability perspective, going back in time when water was plentiful on Mars and the atmosphere was thick enough to support it, those would be key locations to check and see if life had existed there at one time.
I think the most habitable place now, our best bet at finding extant life or life that's currently there, would be underground. I think, again, protecting yourself from the surface is critical. I think sources of water that might be accessible without having to melt or process for organisms currently on Mars would also be found there.
Okay, final question, and this deals obviously with the activities on Mars, and perhaps this is for John Grunsfeld. Dr. Grunsfeld, the Mars program, lots of things going on. Are there any other NASA projects that will help get humans to Mars?
Well, I think there are a number of projects that will help humans get to Mars, starting with the International Space Station. You can't see it in social networking, but in the back of the room here is a Sokol suit, which is the suit that astronauts ride to and from the International Space Station in when they're flying on a Soyuz vehicle. And I had the opportunity to train as a backup crew member for the International Space Station. And when I was contemplating, what I would do for 6 months on the space station, I thought, great, I'm going to pretend that I'm traveling to Mars, because traveling to Mars is probably about a 6-month trip. You'll be in weightlessness the whole time, very likely, depending upon specific architecture, but I'll get to experience that 6 months travel to Mars. And so every time we send a crew up to the International Space Station and they spend 6 months in weightlessness, eating, sleeping, doing other things, living, working in space, they are practicing a cruise to Mars other than radiation, because the Earth's magnetosphere protects us from radiation. But in all other respects, it's a practice mission. And so we're able to test technology for processing water, for reprocessing urine, for removing humidity from the atmosphere, from studying the medical effects. And what we're learning is that in terms of things like muscle and bone health, we're able to keep people healthy now in space. What we've learned from the radiation detectors that were on the Curiosity mission traveling to Mars and to the surface is that the radiation's significant, but it's only about double what you would experience on a long-duration space flight on the International Space Station. But there's still a lot of unanswered technology questions about how to keep, what kind of food should humans eat on these long missions. We're still eating food that's kind of derived from the space shuttle missions that tastes good, a combination of Russian and American and an international diet. But we haven't really asked the question or learned yet, what should be the diet for humans in long-duration space flight, or what should be the diet for Mars to help tune human health and performance to get the desired results we want and have it store for a long time. I actually did an experiment for 2 weeks where I ate nothing but food bars, but we chose those food bars very carefully to have the right nutritious balance and also to bring the caloric quantity way down. I actually was only eating 1,200 kilocalories, normally called calories, a day, but the body adapts very quickly to that and can survive for months and months on that level when you're in weightlessness. And at the end of the 2-week period, the doctors did my blood draw, and they said, John, you're the healthiest we've ever seen you in 18 years of studies as a guinea pig. Keep eating this diet forever, and you'll live a long time. So we're doing a lot of work on the International Space Station. I think all of our future Mars explorers, robotic explorers, will continue to have experiments that help us in human spaceflight. So I think we're going to see a lot more leading towards Mars.
And of course, we can't forget that later this year we have the first flight of our Orion capsule. So in addition to the work we're doing on ISS, we actually have pieces of hardware in production, Orion and our big heavy lift rocket, the Space Launch System, two essential pieces of getting people to Mars eventually.
Okay, ladies and gentlemen, that's going to do it for today. I want to thank our panel here and our previous panel, and again, it will be archived at www.livestream.com/Mars. I want to thank the most visited museum in the United States for hosting us here, Smithsonian's National Air and Space Museum, and to the thousands of folks who have made this day possible with Myrrh. Happy birthday, all the great work, and a special shout out to the Jet Propulsion Lab, managing the programs and doing the incredible things you do in planetary exploration. Again, we want to thank you, www.nasa.gov/Mars for all of the Mars exploration. And ladies and gentlemen, we thank you, and go Mars, go Miss Carson. We'll see you on the Red Planet. Thanks for joining us.